Yes, you're audible to everyone.
Okay. Okay. So last time, the last session, what we discussed was how to get started with exploit development. What were the protection mitigations or mechanisms which are applied on binaries and how they work. Basic idea, right? We had an overview, and while we started, we disabled almost every single one of them, so as to first learn how to exploit things, and the second objective was to bypass the mitigations. Now, in the today's session, what we're going to do is we are going to bypass the non-executable stack mitigation or the NX mitigation, and we'll be seeing at uh, a few options about how we can uh, go about exploiting binaries and getting shell access or getting a shell code executed in case the NX option is set, right? Now the binary would be the same actually. And for you, if you don't know, I'm using 1 to 18.04 in case you are trying to match what I'm going to do, right? So let's see what we have here. Okay, so this is our basic program which we discussed last time. So we'll be keeping the program same, but instead of going out changing the program, what we're going to do is we are going to just let one of the exploit mitigation remain applied and not apply, because if you see the last thing when we compiled this program was disable the stack protection and make the stack executable, as well as make sure the binary is not pi, right? Now this way, this time, since in this session we are going to bypass the NX or the non-executable stack option, we are going to remove this option, but we'll let these options enabled, right? So let's just disable this, and nice. And also let's just disable the ASLR so that things get a little easier. Yeah, nice. So first let's check whether we really have NX on or not. Check sec. And yes, so we have the NX on, and other things kind of partially or not applied. Let's first again follow the same route, crash the application, then figure out the you know offset where the EIP is overwritten and every other thing. So once we get the EIP control, that is when the game starts, because the first objective is to controlling the EIP, right? So to control the EIP, let's just do the same thing. Yeah, let's set the core size, and then Python. Yeah, sorry. Yep, nice. So let's just open the core with the binary, and here we see the EIP is 42, 42, 42, 42. So since the binary is the same, of course, why would something change? But sometimes a few things change because of one or two additional things. Now, in case since the protection was altered of the stack or the non-executable memory areas, we get the same thing, right? And let's see what actually two words in hex from the stack, and we see we have the CCCC just after the EIP overwrite, right? Since this was the 4 bytes which overrode the EIP, and the next 4 bytes are on the top of the stack, which basically means we can do stuff, right? Now let's have a little idea. Yeah. So any questions till now? I don't think there should be any questions because what we covered here is basically what we covered in the last session. So there's nothing new today. Let's start with the formulating what we know. So we have some junk, then we have EIP, and then we have rest of the payload. This is the basic idea that we have for our exploitation. But the thing is, we cannot point. Let's suppose if EIP is pointing to junk, which is shell code, since we are more or less improving upon the last version of our exploitation scenario. This is where things get interesting. Well, actually, let's first see how it actually works. So what we had last time was we already made a Python script which does this thing. And yeah, so RM core. And let's first try what happens if we run this binary with the input of the previous exploit, right? So let's just break on the overflow, run with. There was, okay, I also need to, no, this is one.txt. Yep. And let's set the breakpoint here at the end of overflow so as to follow the return instruction, right? And let's just continue. But before continuing, we also need to know where the data is getting stored. So let's also have a breakpoint at plus 36 and continue. So plus 36, we the push EAX was the pointer to the buffer where the data will get stored, and it is, as we see, it's the exactly same which we found in the last video, that it would be that it was 3F358 and the rest is the same, right? So let's just copy this and dump the data, let's say 20 words in hex. And of course, since there is nothing here right now, as read function has not been called and we have not taken any input, it contains random values, right? What we usually call junk values or junk data. Let's continue, let the read function take the input, and we are at this thing. And see, now we are going to the knob instruction, which was the basically crux of the last video. And let's say if we do an SI and we are at this. So you see the EIP was this, which was to return where to, right? And let's see what happens when the stack protection is enabled, right? The NX is enabled, and let's see what happens if we try to execute this. So let's do SI and we see we get a segmentation fault. And you see here we typed the command SI for a single step, and the program received segmentation fault. The basic idea is because the stack is not executable, or this memory space is not executable. Let's see what are the memory protections for this area. And since this is, we know by default it is in stack, let's see BFF38, which would be here, right? So this is the stack mapping, the start address and end address. And we see the permissions are read and write, but there are no execute permissions on this memory. And since there are no execute permissions on the memory, we cannot execute anything. So is that clear, or are there any doubts? Yeah, I think that is clear. So the next question comes is, so what do we do, right? We have established that this cannot be done, right? Can't do this since the stack is non-executable. So we need to do something, and that something is either we can call, one thing that we are going to do is return to libc, which is basically calling libc functions directly. Now, how this works is, how about we call a system function, and we are talking about the system function and not system calls, right? So a system function, if you have programmed in C language, is a function which takes an argument. Let's suppose we pass it ls or something. It executes it and displays the result. So let's first see how it works, and then we will come back to why we want to call the, or why we would want to call the system function, right? Nano demo dot c. Let's try to execute bin ls on the system, right? Let's just do an ls with the current directory gcc demo.c minus -1 demo, and here we go. So we get a ls. Basic idea. Now, since the system function does, let's try to get it runtime argument just for another demo, right? Now, this is why we are going to be using the system function. So the basic idea here in case of return to libc is, once we get the EIP control, we call a function, right? So let's just set the basic idea here. After EIP control, we are going to do is, we are going to call a function which will either execute our shellcode or give us a shell, right? Now, so let's see what are our options. So to execute our shell code, let's say the challenges, right? Challenges in option 1. The challenge is stack is nx. So solution is change memory protection, right? Like the simplest solution would be the to change the memory protections and make it rewritable executable. And how to do this? We can do this with mprotect function or syscall. I don't know mprotect is a syscall, but yeah, it works fine. So it is a function which apparently changes the memory protections of a page. So we can do this thing, and after using mprotect, so let's see how it works. So how it would work is to just EIP mprotect and jump to shellcode. This would be one solution. Let's say challenge the second solution. Actually, there's no challenge, more or less. It would be more of a route to second solution. or actually option. We want a shell which can be taken using uh, the system function. And since we have the shell now, no need for any shell code. Right. I don't know if there could be a third option as well. Might be, but these are the two options that I see, and I believe these are more than enough, right? So, and since the second option is far easier, and at the end of the day, what a shell code would do is this shell code. Let's just write here. The shell code uses shell, but we already have the shell in the second step, and here we have the third step, shell. And we also need to deal with the shell code address and inconsistencies and every other thing, and here we don't have to do anything. So what we're going to do is we are going to take this route, the second option, and we are going to call the system function with the with proper parameters, and then once we have the shell, it's game over, right? So any questions still here?
No questions, I guess.
Okay, that is pretty good. Okay then, so this is what we're going to be implementing now. There are a few things if we want to implement this. So let's go about implementing the solution, implementing the second route to shell code. Shell. And this is where a few things come in, right? So thing is, how do we actually go about calling the system function from just having access to the EIP? I mean, yeah, you can just put the address of system in EIP, but the first question is system function executes even if the stack is NX. So well, the thing is, yes, it does. To demonstrate, this is a program which works, right? The demo program, and let's just have the properties checked, and we see everything is applied here, right? So see, the system function does not execute anything which is on stack. The system function is a function which is already in the executable memory. So yes, it works. Now this is what we are going to call, and this is why this approach bypasses the NX protection, because we are not going to change the protection. I mean, yeah, we can change that, but that basically defeats the actual purpose or the actual protection idea, right? Now, going with the actual initial idea, what we are working with is we call the system function, and the sense that it is a function and it is in the C library code, and that code is executable. So we are not working with stack anymore. We are just returning to a code which is in C library, and that is why it is this attack or this attack vector is known as return to libc. We are actually returning to C library from our compromised function or binary or something. And since the since the C library or the any other code which is mapped as a executable code is meant to be executed, there are no segmentation faults, there are no problems, there are no system violations, right? So is that clear? Yeah, okay, it's clear. Now to do this, returning back to our thing, to get a shell we need two things. Well, to execute system bin bash, we need two things. First is address of system. I mean, that's of course, obvious, right? Address of system. So put it in EIP, and we just cannot call system without any arguments. The system function requires an argument, and since we need a shell, the argument must be a pointer to a string which is null terminated, as well as, well, points to the binary which we need to execute, or which needs to be executed by the system function. So we also need address of bin bash, right? Now it can be done in a few ways, right? In a number of ways it can be done. One is, since I'm using the Z shell, I can actually, let's have a shell. I already have a environment variable which is pointing to the current shell, but let's not use this. Let's use the bash just to see the difference. And if we want to see this, it can also be done, right? The procedure would be exactly same. We will be looking at how we are going to call the bin bash, right? And once this is done, once this has been done, we need to see where system returns. And usually if you don't want to, point it to a memory location which is not really a code or something which can get the program crashed, well, that might present a core or something. So we want to, if you want to terminate the process without any faults or anything, we, or you can actually call the exit with the 0 as the parameter, right? Or exit with 1 or 2 would do, there's really no problem. The thing is, if we call actually exit after the system call or system function call, the binary will exit cleanly without any crash. So that is one thing that we also can do, right? Now the first thing is, let's see this thing. So try to figure out the first thing, address of the system. Now let's just load the GDB. And now since everything has been loaded, let's see VM map, and this is the glibc mappings, and this is where glibc is. This is more or less the only thing which is readable and executable at the same time with glibc. Other things, this has no permission, this has read permission, and this has read and write permission. Okay, so this is the only thing that has executable permission. So to print the address of a function, we use the PO print command of the GDB, and let's just give it the function name. And we see this is the address of system function. And let's say at the same time, let's do the exit. These are the exits. These are the addresses of function calls, or the functions. And let's see. So B7E1C2, B7E, right, falls in this range, and B7E0, yeah, falls in this range. So both of these functions reside inside the GNU C library. So that one thing has been accomplished, right? Let's just copy this and put it here. Let's just make sure that we have this on the top of the screen, and coming here, let's just have the address of exit. Now we have these two things. Now the next thing that is required is the address of bin bash, and we are going to do this using an approach which is not really that clean. It really takes a little bit of effort, but gets a job done, because we can also get other things inside of it, right? For example, let's see. So what we're going to do is we are going to export an environment variable which will point to a string which need to get executed, or command to execute. Basic idea. So to export something, to set an environment variable, we export, let's say, my shell and bin bash, right? So let's see if it has been there. Yeah, so we have already exported my shell. So this is the thing. Now, when a program executes, there are three things. If you know, and main, right? So there are actually three syntaxes. One is this default one, another is this int argc and char pointer to argv, which basically is the runtime argument. And the third one is main int argc argv and a pointer to environment variable. This is the one thing, or this is the actual syntax. If you don't provide the third argument, it inherits the environment variable by default. If you don't provide anything, this is the same thing you can use. It's the same thing, right? So what we're going to do is we are going to, and since the environment variable, if we do not provide anything, is the default one that is used, which is inherited from its shell, from where it is executed. And here we have already exported one variable which is pointing to the shell. That thing is also going inside the memory of the program or the target binary. All we have to do is to find out this bin bash inside the program's memory. Now, one thing that we can do is we can write a program which takes a runtime argument of the environment variable name and returns the string at that location. So we do this using the function get environment. So what get environment does is it gets the value of, or it returns the value of an environment variable. So here I've just written this. It's a very simple code, right? So get address nx and my shell, right? And we see my shell is at this address and it contains bin bash, which we have already established, or which was the actual value which we exported, right? So now another problem is what can happen since the environment changes, right? Or not really changes it because of various factors. It gets, more or less the offsets change a few bytes or something. The string bin bash would be somewhere around this address, right? So we will be looking at this address and figuring out whether the string is somewhere there or not. So let's just do the same thing. Should break the overflow and run this with a 1.txt, and yeah, so we are inside our program's execution. Now let's see what the address was. This was the address, and let's print the string at this address. And there's no more strings. Let's just go a few steps back. Let's go there, right? And here we see. So this was the exported environment variable that we had, and it is at AF, sorry, 8F, not BD, which the shell reported. And this is the only difference that is going to be there, the difference of offsets. Now all we need to do is to put these few addresses. And yeah, so since this address is going to be as the parameter, the string from this address is going to get executed, we need the address of this, sorry, actually this, and not the my shell equal to part. So from 8F we need to do 9497. sorry, 97, yeah. So this is the actual address of the string inside our memory, and you will see in a few seconds that of course this address is also wrong. Now, can anyone tell why this address is also wrong and this is not the actual address of this bin bash inside the memory of our vulnerable program? Let's just do this, and we don't really care about this thing because it does not matter whether there are knobs or there are A, B, C, D or whatever, because we are of course not going to do anything about that thing, right? So you can have just 516 bytes of A's right there instead of knobs, and it would be the same thing. Now this is what we are going to do. So the EIP will be pointed to, and sorry, before explaining that, let's have a look at how the stack or the how the data for the stack will be arranged inside memory. So top of the stack, top of stack, right? And here the first thing we are going to put is sorry, let's go to the EIP, right? So EIP is system, sorry, system, and the return, because it is a function and it needs to return something somewhere after the function ends and the return syscall is going there. So the next thing that we need to do is the in the place of 4 C's that we used in the crashing demo, we are going to exit, and then there will be argument of system, which would be pointed to bin bash. So we need to do a few things. The system address of system is this. Sorry. Let's just do it this way. Let's just already pack it, right? So we get saved the burden of typing again and again. Our exit is going to be, uh, yeah, and where's the address of exit? Yeah, here's the exit. And we're going to put it this way. And the next return of, or the address of bin sh is going to be this way. Let's just align them properly, right? And this was the address that we found out, which is going to be here. Red sys plus red exit plus bin sh. And this is going to be what we are going to do. And let's just dot exploit one demo next.txt. and it says this command not found. Now what we can do is it seems to be confusing.
Sir,
Yes.
in that Python file,
Yes.
exit and bnsh address is same, I guess.
Let's see. I might have made a mistake. Oh, yes, that was the problem. Thank you. It did not get copied. Sorry. Next. And here we see a few errors that this command not found, this command not found, and this not found. So any ideas? Anybody who wants to make a guess why when we are providing the address of bin bash, which we already figured out, the exact address, we provided the same and it confuses them for some other things. Any ideas? I don't think anybody wants to attempt. So, see, the thing is, as we saw in the last session, things or the environment inside the debugger gets a little bit changed because there are a few environment variables which are added when the debugger is working on your binary, which makes them extra, and that is why the offsets differ. So we again need to use the debugger and locate where these are, right? So let's just do break overflow, since it does not really matter. Now our address was this, and we see it is the same thing, right? The address is the same, but it is saying that at this address we have this command, right? So let's see where this command is. Yeah, so we have this command somewhere about here, and there's a star.spx. Yeah, 36 star.xps and xspf and 36. Yeah, so this is more or less where we have this thing. Okay, 36 is there. So this is where the so this is the command that is getting passed uh, to the system function. So the simple idea is to figure out the offset and perhaps add or subtract the offset to get to the actual location. Now this is what we have, or this is the address that we are that sorry, not we, the system is confusing with this address, right? So that means if this is getting translated into this thing, we need to figure out the difference and we need to add the offset to the original thing, so it will go back the same amount of bytes. And we can do this. Let's see the difference. Let's just print in decimal. The difference is of 37 bytes. So we need to add 37 to this address. So we can work on this, right? Control Shift C. And this is the address that we need to put inside our script. So let's try with this address. Okay, there is something problematic. No, it is working fine. So the return is, the exit is getting called with 10. The reason being, so let's just have it with the same thing and get one of txt with wait, there is no one.txt. Yeah, okay, so the problem was something else. Yep, one.txt, and we have this get and unfortunately for some reason our shell code or our payload is not working. Let's have a look at the GDB, why it is not working, right? '86. Continue, and here we see the return address is of the system, but this string is, so there's a problem with the string offsets. And after that, since the system executes that thing, what we get is the exits is called, and this is where the problem is. And if we go back to this location, and I'm pretty sure that debugger will display this as the actual string which we want to execute. Yes, so this is the, let's just have something with, let's try to increment or decrement something, right?
Hello, sir.
Yes.
Yesterday, I think I also faced with same problem.
Yeah.
When I going through with GDB, I check the correct address and put in my script.
Yeah.
But when I'm running my exploit, it's showing that my main means my shell code is not pointing to main.
Sorry.
Then when I check the dump of code file,
Yeah.
they're saying that no idea how, but that means the address it's showing to point in the GDB that it's pointing to shell code. Now there's not a shell code. After something like I think 5 to 10 bytes later, it starts. So directly I put to that address and it works. So maybe in this case also it's happening like.
Yeah, so these inconsistencies are more or less about or because of the environment differences. So as I told you, environment differences, if we scroll above, we, sorry, yeah, here we have it. Yeah. So there we figured out, if you remember, before this thing, right, we put the actual address of the bin.sh, but since the environment was a different environment inside of GDB and outside is different, so
Yeah.
what the argument to shell or the system function went was this thing, and that is what we did to something else. So this is a bit problematic. Let's just have something else, and let's just have an argument to exit as well. Exit 0 would be, sorry, yeah, back, just for the sake of consistency. Let's make the exit with 0, though that wouldn't do almost nothing to change the scenario, but let's just do this thing. And see, this is the thing now that is showing that this address, what we went with, AC, right? So it says AC is the address of this star XPF. And let's see what happens in case of GDB. Like, let's say overflow, run with. And let's see what is at this location, right? AC is this, but 7C. So let's have a look. This sounds familiar. This is where it came from, right? So XSPF 0, and there was 36, 7C, 7F, I guess 81, right? And this is the 81, which is perhaps being passed here. Actually, besides the 80 is getting passed. Yeah, so this is the input this is the pointer that is being passed, and apparently a pointer actually is here. So we again need to figure out a few distances, and this is the time taking process of this demo, right? So minus, which is 80, which is about 17 in hex, and let's just add that 17 in hex to it, which is AE, right? So I'm not really sure whether the AE would work, but yeah, let's give it a try with, yeah, no, AE would not work. I don't really think AE would work. Okay, so I feel we are having a few calculation mistakes. And now the at AE was dot XSPF, which is at 82, if I'm not wrong. Yeah, so this is the 82 thing. A string is still here. The difference is 15, right? It says AC, and let's just add AC to 15, that is C1, and we will see if it works fine or not. And no, it does not. So this approach is, as you can understand, is pretty bad. Another thing that we can do, and which also does not you know make us export a variable or something, is to figure out whether there are already some things sorry, actually, or some strings inside the binary, right? Let's just run it simply, and let's use a command find. I think find is the command. Yeah, so let's find. It takes, yeah. So let's see if we can find the bin sh inside the GNU-C library, right? So find, okay, I don't think that is the actual command. So I think search is one thing, then sh. Okay, so search does a regular expression search, and let's do Jeff help. Yeah, so search pattern with yeah. So the command actually is the search pattern, and we search for bin inside the process memory, and you can see that there are two different sections. One is in the GNU-C library and another on the stack. So we already saw what are the problems with the stack part, right? See, it still states that it is 97, but it is not actually 97. So instead, what we can do is, how about we take this address and use it, right? So this thing is already inside bin sh. So let's do this. Sorry, inside the glibc. So let's just use this and see what can work. Control X, and it works, right? So this was the second approach which I was talking about. The first thing is going about exporting the variable and then figuring out the address, and then more or less the trial and error approach to see how much the offsets differ or not. And the second thing is, well, we can actually search whether there are any other occurrences of bin sh or any other thing, and we get the shell, right? Since it is inside the glibc by default, so you don't even need to worry whether, well, you don't even need to export it, right? Any questions?
Sir, initially you had found that 97 address from your temporary uh,
In our
binary.
variable, yes.
In that binary, initially you got something around AD, and you you told that we need to search, and you changed it to 8D, and we saw that bean sh was and bean bash was present at that place.
Hmm.
Like how how did you matlab, how did you got to know that
You
a
can ask in
AD
Hindi.
to 8D?
8D to 8D.
Like
Like,
in 64 it's if you can say, like if it was a pointer, then it was like a you would have changed the 8 bits, like
okay. So are you asking when I went from the this address and then from here to figuring out where actually was the bin bash or something else? Are you asking?
yes, from there here only, how did you able to
Yeah.
find
So
that?
it is quite simple, right? So since we know that, well, since our program told us that bin sh is at this address, or actually bin bash, so let's figure out what is at this address, right? And we see that after this there is no memory because this is the top of the stack, actually the bottom of the stack, right? So this memory is not accessible to user mode and we cannot access. So anything which is there should be either before it or after it, and we have already seen that after it there is no memory or there are no strings, right? And there is no fixed way, right? You can just, let's say, let's go back a few, let's write 3, right? And let's just coming to the point till we see these things again, so that we see that wherever we went in before, we have covered everything from there to here, right? This is the way. So in case you don't find this here, so what we could do is instead of 3D we can make it 1D and then come back. And in case it does not work, let's say keep it 5D, but if let's move back one step, ED, right? So we can do anything. You just have to keep subtracting and printing the strings till the point you see your shellcode. Sorry, not the shellcode, your string or the command which you exported. And once you have seen that thing, you just have to find out where it is in memory properly. And the next thing is, when you put this address, as we already saw what happens when we just blindly put, or not blindly put this address as the argument to system, it for some reason goes to these things, right? And then it keeps going back a few bits, so we then need to adjust for that byte. So what we were trying to attempt here was, if this was getting resolved to this address, because for some reason this address or the address of this part was pointing to here, right? XSPF0036, and that was the actual problem, right?
Okay, sir.
So then you need to keep incrementing it, because if this address points to, let's say, this place, you just have to increment this many bytes so that it gets adjusted to these many bytes and then it points to here. Now this takes, as we saw, it takes a really lot of time to really adjust stuff and make it work. So instead what we did was to search for the same thing inside our memory, right, inside the binary. And we figure out that bin sh is, well, actually it is already loaded inside, or it is already stored inside the glibc binary or the glibc shared object. So let's just use this. And since it is not on the stack, right, well, I think it is on the stack but not on the process stack, some other memory. So what happens is, the environment variables do not really affect it, and since they are not affecting it, this address does not give us any problems. And the moment we put it inside our binary, right, in our exploitation script, we wrote that here, and after that it works without any problem, as you can see. So is that clear?
Yes, sir.
Yeah, okay, cool. Any questions? Okay, I don't think there are any more questions. Animesh, are there any other questions or something else?
Nope, I'm not getting any questions so far. So
Okay, so to wrap it up, what we did was today we saw that how to, yeah, so we essentially saw how to bypass. Okay, exec stack, or you can say the NX protection. So since now at this point, if you scroll above, right, at this point we have a shell, you can do almost anything. And that is the basic crux of this thing, of this second route, right? As a as an exercise, what you can do is you can try and attempt this first idea, which is to use mprotect and then jump to the shell code, which would be more or less the same thing, right? Here we called here we put the system as the function to call, and in this approach what you will do is you will put the call address of mprotect, and after that this is the pointer to bash, sorry, bin bash. You will put arguments to like argument 1, argument 2, argument 3, and just like that it will work, right? And once you have written all the arguments to the function which you are going to cover here, to call here, the argument to exit will come, which would be 0, as you can see. Sorry, yeah. So this is the return status, exit 0. So you can do this thing, and this is why sorry, and this is how you can actually go about doing things. Now instead of instead of having exit here, what you will do is you will just address of shellcode. So when this mprotect returns in your homework, when the mprotect returns, it will jump to shellcode. So this was everything that we had for this session. And in case you have some other doubts, or might be you want to attempt anything, you want to recreate this exact material or exact steps exploit that we covered here, and you've encounter a few problems or some problems, you can ask anytime. I would be happy to help. There is really no problem in case you are attempting it yourself and you find you are stuck, right? So don't hesitate and try it yourself. It is actually pretty easy, right?
okay, so let's wrap it up here. Anyone having any questions for us? Like any suggestions that you want us to cover in future? Anything? Okay, as usual, videos will be available on YouTube. That's like every single time we got the same questions. Okay, and yeah, that's pretty much it. So thank you guys for joining in today. Tomorrow we have sessions on malware from Mishra ji. So tune in. You can actually register for that. We already have the link shared up with everyone. If you did not sign up, you can just go and sign up here. When web application pen testing session going to be conducted? For web application, we are looking for some speakers who can talk. If you don't find any, I'll start giving you training on DBWA. That's okay. So actually, I'm just having some talk with other people, so we can have some challenges from CTF.live or Pentester Lab. So once we get confirmation from them, we'll try to include some sessions from those places, or we can have our own lab setup and do it from there. So it will take time. Okay. So rest assured that will be there. And for malwares and exploit development, apart from that, you need anything, like any other topics, how to hack Facebook, Instagram. If you need these things, please contact me. I'm happy to help. Windows exploitation, if possible. Windows exploitation, we're thinking about having that as a paid course. So I'm not sure how comfortable we are to having these things. We can have 1 or 2 sessions on that. Okay. So that won't be any issues.
So any session on antiviruses, like how to learn how it's working internally to block some functionality
Um,
and bypass?
you want us to train you or like show you antivirus bypass or how antivirus works, like workflow of antivirus? Which one?
Like how it's working and how to bypass them if someday like some mechanism comes in an antivirus that is preventing doing stopping us from doing something on that OS, then how to understand that what it might be doing, like it it won't be publishing it publicly, like what it would be exactly doing inside, so then in such cases how to proceed and
Uh,
do stuff.
I can arrange a demonstration on about Windows inbuilt firewall like that we have in Windows 10. So we can have a mimic as, and I can show you how they are blocking it and how to bypass it. So that is possible. We'll look for that one. That's a good topic. Okay, so yeah, that's all I think. So see you guys tomorrow with Ms. Raji. So have a nice time, stay safe, and as for new updates, the lockdown is extended till 30th of this month. So yeah, we're going to have a lot of sessions on every single day. When will the next digital forensics session? Wait, that guy is still here. Tej, can you unmute yourself? Oh, I'll confirm with him and update you people. Okay, so are you in our WhatsApp group? If you are, we already shared one course that is 8 hours long. So you can follow up that. And for our sessions, we're actually working with Tej and other people's. So we can see. Okay, so Tej will be taking care of DFIR here as soon as his system is ready. But because of the extended lockdown, I'm not sure how it's going to possible. Okay, so that will be the thing. And I'll really appreciate you people if you can go and sign up a feedback for us. So that just make us, looks good. So where is the feedback form? Please fill up this form. Okay. So that's all we have for today. And let's see what we can do tomorrow. So have a nice time. Stay safe. And we'll see you on next time. Bye. So Himanshu,
हाँ भाई
wrap up करते